You know, what if I told you that the most revolutionary ideas in computing aren't in some far-off future, but are actually buried in the past? That's what we're doing today. We're going to go digging for some profound, almost forgotten wisdom from computing's own history, and believe me, these are ideas that could totally change how we think about technology. So let's start by figuring out this mess we find ourselves in. Now get this, this isn't some critic from the outside looking in. Nope. This is a pretty startling confession, and it's from the very pioneers of computing themselves. I mean, they're basically telling us that the path we're on, this whole mess, it didn't have to be this way. It wasn't inevitable. It was a choice. And, maybe, just maybe, it wasn't the best one. And that, right there, is the heart of the problem. Our industry is just obsessed with the new thing. The next big thing, the shiny new toy. It's basically a pop culture always chasing the latest trend and completely ignoring its own incredible, revolutionary history. But what if the answers we're all looking for? What if they're just sitting there gathering dust on a shelf?
All right, so let's do it. Let's just escape the present for a minute. We're going to head all the way back to the 1960s to check out a couple of absolutely incredible ideas. And I'm not kidding, these are concepts so advanced, they still feel futuristic today. They point to a completely different path, a whole other way we could have been building our digital world.
Okay, so first up, we've got this system called Sketchpad. We're talking 1963 here. And it introduced a way of thinking that just flips programming completely on its head. It's called relational programming. So think about it like this. Instead of giving the computer the super rigid step-by-step recipe it has to follow perfectly, you just describe the relationships. You lay out the rules, the constraints. You tell it what you want the end result to be, and the system is smart enough to figure out the how all by itself. And this just lays out the difference so clearly. On one side, you've got how we build most software today, programming by instruction. It's just a long, brittle list of commands that can break if you look at it funny. But on the other side, that's the Sketchpad ideal. Programming by requirement. It's flexible, it's robust, it solves for an outcome. I mean, just imagine if we could spend our time debugging the requirements instead of the code. That would be a complete game changer in how we build things.
So right around the same time, another pioneer, a guy named John McCarthy, was tackling one of the absolute hardest problems in computing, one we still struggle with today. How do you manage change over time without messing everything up and corrupting your data? His answer was this elegant idea he called a situation. The easiest way to think about it is like a perfect, consistent snapshot of the world. Every single fact is time-stamped, it's tagged with the situation where it's true. This lets you move from one totally stable state to the next with, and this is the key part, zero risk of corruption. It's beautiful.
Okay, so these ideas from the past, they're not just cool historical footnotes, right? This isn't just a history lesson. Buried inside them are these timeless principles for building systems that are not just robust, but can scale up, like massively. And the key to unlocking that kind of scale, well, it requires a pretty fundamental mental shift away from how we usually think about building software.
And this quote just nails it. You have to get away from this idea of software as a set of perfectly meshed gears, where if one tooth breaks, the whole machine grinds to a halt. Those systems are just too brittle. They just don't scale. The alternative? Something much more like messaging. You have independent parts, independent components that just talk to each other without being so rigidly locked together. And really, if you're looking for the best model for this kind of system, just look at biology. Look at us. Our bodies are made of trillions of independent cells, and they all communicate using messages. Think about it. When one cell dies, does the whole system crash? Of course not. That fault tolerance is baked right in. It's not some add-on you bolt on later. And it's a design that has proven it can scale to a level of complexity that is, frankly, almost impossible to even imagine.
So that brings us to maybe the biggest scaling problem of all time. I want you to try and imagine this for a second. The year is 1963, and you have just been given a challenge. Connect every single computer everywhere on the entire planet. Where do you even start? How do you even begin to wrap your head around a problem that enormous? Well, the answer is you don't. You ask for something even bigger. And this is genius. When J.C.R. Licklider was faced with this exact problem, he didn't ask his team to build a planetary network. No, he asked for an intergalactic computing network. He knew that if you ask engineers for something that huge, they'll inevitably scale it back down to just the planet. And that right there is the core principle. You design for the galaxy, and then you scale it down to the planet.
See, by aiming for a scale that seems completely ridiculous, you force yourself to solve all the really hard problems, like fault tolerance and autonomy and communication, right from the very beginning. Because if you can figure out how to make it work across galaxies, well, making it work for a single planet suddenly seems like the easy part. Which, of course, bring us all the way back to today. Now that we've seen what was being thought about 60 years ago, what was possible, we have to ask ourselves a pretty tough question. Are we even working on the right problems? Maybe the biggest challenges we face aren't technical. They're not about faster processors or bigger hard drives. Maybe the real challenge is philosophical. So let's just put the question out there, directly. Forget about the tiny incremental improvements for a second. What are the truly fundamental, the really big, unsolved problems in computing that we should be pouring our energy into right now?
Because here's what happens all too often, right? We get stuck. We get completely lost in the weeds of a subproblem. Things like how to process the data or how to store it or how to move it just a little bit faster. And we get so focused on that we start to mistake the means for the end. We totally forget what the actual goal was in the first place.
And maybe this is where our focus really needs to be. The real challenge, it's not big data, it's big meaning. It's not just about managing these ever-growing mountains of data, it's about finding the actual meaning buried inside it all. So what if our goal wasn't just to build bigger and faster machines? What if our true goal was to build systems that help us understand our world and ourselves in a much deeper way? Just think, what would that future look like?